Okay, so at the turn of the 19th to 20th century, so around the year 1900, we thought we had figured out pretty much everything. And there were only a couple of little details that we didn't have right. That was the general feeling at the time, and I don't think you'd have found a lot of people who thought differently. Obviously, they were really wrong. Everybody was extremely wrong. And the break between the two of those two things is what separates what we call classical physics from modern physics. And so modern physics starts with something called blackbody radiation, and it starts with a man named Max Planck. So the Chinese have known about fireworks for thousands of years. We burn different metal powders and they burn different colors. If you want green, you burn copper. If you want blue, you burn cobalt. If you want red, you burn strontium. They didn't necessarily know what these metals were. In fact, they didn't know what those metals were a lot of the time, but they knew that different salts and different materials burned different colors. But if you take a lump of copper or a lump of iron or a lump of cobalt and you stick it in an oven and you start to heat it up, they all start to glow red at the same temperature. And nobody knew why. We knew it was true, but we didn't really know why. And they all start to behave in the same way, in that when you heat them up to a certain temperature, they all glow the same color red. You heat them up some more and they become white hot. You heat them up even more than that and they can become a bluish hot. And so it was in the 1800s that scientists had characterized what colors of light, what frequencies of light were coming off of these things as they glowed. And they ended up with a bunch of curves. When you graph them, they look like this. Now, these are a bunch of curves for 3,000, 4,000, 5,000, and 6,000 Kelvin. And at each of those temperatures, you can see the band for the visible light, what we can see, and then you can see ultraviolet on one side and infrared on the other side. And as you heat things up, this graph becomes pointier and it becomes broader off to one side. So if something is glowing only enough to get some red there, then it's going to be red hot, or if it's mostly red. So if you look at that 3,000 curve, it's mostly red. Whereas when you look at the 6,000 curve, it's really through the whole spectrum, and so that thing is white hot. In order to get something so that that peak keeps shifting to higher and higher frequencies, to get it so that blue overwhelms things, so that it's a white blue, you have to get things much, much hotter still. So in nature, there are stars, for example, that glow blue hot. We know exactly what temperature they are because we can look at them through a spectroscope, and when we do that, we see that curve for blue light. We know exactly what temperature that is. And so we can look around the universe and see how hot things are. And so things glow red hot. Black holes can glow X-ray hot, which is pretty neat. We built the Chandra X-ray telescope to look at those because the accretion disk of stuff that's getting sucked into the black hole is getting sped up so fast that things are rubbing past each other so much, they're making so much friction that they are not red hot, they're not white hot, they're not even UV hot, they're X-ray hot. So it's pretty neat stuff. So anyway, if you look at this curve, if you look at this graph, you'll see that it peaks. You've got this nice real peak at 6,000 Kelvin. Well, guess what the temperature of our sun is? It's 6,000 Kelvin. And so that nice orangey light we get from the sun, it's really pretty white, and the orange comes from atmospheric effects. The light that comes down to the ground is mostly in the visible spectrum, which makes perfect sense if you realize that the eyeball evolved on planet Earth. We evolved to see most of the light that's there. So, this was a puzzle. Why, when you burn things, do they burn different colors, but when you heat them, they all glow the same amount at the same time? That's the question. So mathematicians tried to model the shapes of these curves, and this is what they got. Notice the difference here between what was expected and what the data showed. Clearly, something was very, very wrong. So this classical prediction is called the Rayleigh-Jean law, and the Rayleigh-Jean law has a really big problem with it. It predicts that as temperatures get hotter, as the frequencies get smaller, energy approaches infinity. And you can't have infinity energy. There has to be a tiny amount. And so this curve needs to go up, and then it needs to trail off as you get to really high frequencies, not just go up and then keep going up forever. And that was a really big problem. So Planck really wasn't any more successful than anybody else at characterizing things until, in a fit of desperation, he just said, you know what? Let's, instead of trying to make this a smooth curve, a smooth function like you could do with any other math, let's instead break it up into tiny little chunks. If we break it up into tiny little chunks, let's see what the curves look like. And when he did that, he found that he could model the curves exactly. And that was pretty cool. But he was correct in his modeling. He looked at it and said, that's awesome. But he said, you know, someone who is smarter than me is going to come along, and you know what they're going to do? They're going to do this better with the right math and get rid of the chunkiness. Just, my math isn't good enough. Someone who's smarter than me is going to come along and get the math right. And he was kind of exactly wrong. Someone who was maybe smarter than him and maybe not, you may have heard of Albert Einstein, 5 years later realized he explained something else using Max Planck's idea that energy comes in little chunks, which Einstein called quanta. And this was the birth of what's called quantum mechanics. So it turns out that the reason why Planck couldn't get these curves to match exactly right without breaking them up into a bunch of little chunks of energy is because light comes in little chunks of energy. It comes in little quantized packets that now we call photons, because that's what Albert Einstein named them. And so Planck was wrong. Someone better at math didn't come along and fix his math. Someone who wasn't as good at math came along and fixed his theory and said, hey, the reason why this only works if this stuff is chunky is because it's actually chunky. It comes in tiny little bits. So now we know that Planck's curve isn't a curve at all. It's like a tiny little staircase with each little step being a chunk of energy. How big is that chunk of energy? Well, it's on your reference tables under the equation E equals hf. H is Planck's constant and F is the frequency of the light. So the color of the light, the amount of energy that it holds, is equal to the frequency times a constant. It's a very, very small number. It's 6.63 times 10 to the negative 34 joules per hertz. That number is so small that the steps on this curve are so tiny that the curve seems smooth to anything as big as us. In a similar way that your table or your chair, the wall, feels smooth even though it's made of a bunch of teeny tiny atoms. It's just the atoms are too small for us to notice their granularity. Same idea here. The energy seems smooth from our perspective, but it isn't. It comes in little chunks, little quanta. So what problem was Einstein trying to solve? He was trying to solve something called the photoelectric effect, which photo means light, electric means electricity. The deal is you shine light on metal and you get electricity off of it. But the behavior of the photoelectric effect was really strange, and it really didn't fit with classical physics at all. And so Einstein's explanation involved this chunkiness of light, that light travels in tiny little packets, little bundles. What's weird about the photoelectric effect and how Einstein resolved it is a topic for the next video.